This has been developed by a project funded by the National Supercomputing Mission. And the project investigates around different right here, coming from 6 different institutes in the country. So this is the publication that has come out of this work, where the students who have contributed to the application are also listed here. And as you can see, it's a large team. And we have also thanked the previous students who have contributed to this project. So the entire team would run into more than 40 people who have contributed. This paper is published just a few months back. And so what we show now would be having some of the things from not in its entirety, but with some videos. So which is something a little bit more dynamic than. So this is the team, one of our launches in AIC. We had this picture taken. So every workshop we usually launch the version of MicroSim. So the launch is done on the last day before we close the. And so here we have such event. So this was one of those, I think, good regions where the maximum participation was. And all the 6 groups have been. Some of them are really problems. This is the institute that have contributed to MicroSim. So Avik is the PI and the rest of us are distributors for this project. Here in this workshop. Shashwata has presented from remotely. Vaishalisha's presentation was done posted. Okay, so I encourage you to bookmark this URL. This is the GitHub public repository. We have 2 websites, GitHub.com. This in India is one where we have a code. And then we also have microsim.co.in website where we have links to the recorded videos of all the workshops which are there as playlists in they're all placed there. And you also have some documentation. They are cross linked to reach one of them, the other one also. So, what are the various kinds of models that are there in which are taking particular population time? You see here on the x-axis is there the length scale. So, at the width scale, you have got the component. And sub-nanometer, you have got the atomic phase that are important. And material science spans the entire length scale, so almost 10 decades of length scales. 10 orders of length scales are covered by material science. And in terms of time scales also, we have got from picoseconds to several days of simulation that are happening. So, for example, given element simulations take the actual times as several days. Then you have got microstructure evaluation, which are available. So, as you can see, among these various techniques, phase field is one, which is somewhere in the middle. It's a mesoscale modeling technique, and with this physics happening at milliseconds or much finer than that. So therefore, it's actually very tricky. At the top right corner, the tools are all developed by the mechanical community, and at the left bottom corner, the tools are developed by the physicists. So in the middle is where we have got a gap, and the phase field is coming right in the middle, and therefore the MicroSim committee has to take initiative and develop these tools, and that's what is happening to the launch of. Okay, so what are the latest tools that are available at this space? If you look at the names, they are available. So Abacus answers to 8 concepts with multi-physics simulation tools that are available. And at the bottom left corner, we have got master and constant stressor, which are for electronic structure calculations. They are also available in source mode. Not free version, but at least commercial license, but open source mode they are available. Whereas MicroScript tools are available both open source as well as and for non-running slams is like a bit of standard. So when you look at these tools, there are some different standards how you can solve the problems at macroscopic or electronic level or in the level. But we must take, we don't have such an effective standard yet. So there are tools that are there. MicroSim is a commercial software from Germany, and it is for the computer, and they have got open space, which they get from Germany, which is security based source based code, and based on the results. These are also based on, you can note that these are having limited capability. They sometimes lack thermodynamic coupling, like OpenPay, I think, and sometimes they are not scalable to any large number of cores, like for example, so on. I don't think any of them actually support the GPU. So definitely there is a gap. So we then look at this and take up the process for MicroSim to see this. We making the enhancement method grow much further in the. So the general form of the model that is implemented in many of the solvers in here. We have got extensive discussion on the and KKS models already. So we will not discuss much about the model itself. We look at MicroSim. So in our analytical lectures in this workshop, we have shown WBM, KKS, and GT models. So you have got good overview already. Okay, so what are the kind of simulations we will see in these videos? So the first video shows you a injective, generally injective three-phase, which is seen from the direction looking down as the front is moving towards you. And as you can see, the microstructure is evolving to another reorganize the table to calculate that. It's like finish, you will see that the yellow phase with the contain the red and the green ones between them. So there's a lot of physics that was understood through these simulations by way of how the rod to laminar transition, a continuous phenomenon will go across the phase patches that will be tested the phases. So as you can see now, it should come out. So between the blue phases, the red and green are organizing, themselves are alternating. So similarly, many such simulations were done. Here we have got this report, and we have also got three-dimensional granular. So many of these simulations are actually very time consuming. They are in three dimensions. They will take 10 to the power of 9 or more number of grid points and have at least about half a dozen variables that are computed. So when you multiply, you will see that the number of degrees of freedom is 10 to the power of 10. So it's a huge task. You will need efficient algorithms to complete, and that's exactly what is happening. Like this. So here, MicroSim, the various components are we already covered this little bit during the thermodynamic coupling I think so. That part is the alpha-based coupling that is already available in MicroSim. So, but here also you can see that MicroSim suite of tools is covering almost all aspects of the basic simulation. Like it covers various models. You have got the grand potential model, you have got thickness model, you have got the Gaussian model, you have got also the orientation algorithm model to tackle brain growth without the situation of having to make one order parameter per brain. Like that, a number of models are taken into account. And when it comes to the numerical methods, then the direct difference method, effective spectrum methods, and poly method, they are all in terms of hardware, you have got the GPUs, CPUs, multi-core CPUs and also a hybrid environment of both. So all of these are covered. And we have got both post-processing and pre-processing, and that is used using the Python tool. And there is also the post-processing also used for visualization. So some of the simple analytic output as the grain size as a function of the time, time dimension, and so they are actually plotted readily for us. So as you can see, the MicroSim reflects all aspects of the computation and the ecosystem that we have today. And in that sense, it is quite comprehensive, and some of them are very unique. For example, ability to talk to someone with databases and then running on this combination. Actually, there is no software that can be. It is only software. There are some unique features also which are there in that. Okay, so look at the state of the art for these tools. You see that the existing open source software for the physical simulation like most algorithms, etc. So they are limited by the kind of models that we use and lack of flexibility, choice of distribution, and also the hardware. So, for example, GPU is not possible. Mostly is for easy. So, on the other side, on the commercial side, you have got the software which are actually very expensive, but very limited in terms of their capabilities. So definitely there will be the capacities forward. So what are the various models? Here is one like try to take the original models where they are proposed first. So the multi-component GPU matter, the KKS. So these are the original data that we can look up to know the physics what is GPU. And the thermodynamic coupling is thanks to Pi alpha library and also sim Pi, that is symbolic method. So definitely there is a certain development parallelly happening in the open source community that will help to be achieved. So without, let us say, symbolic Python Pi alpha, we would not be able to do the thermodynamic coupling. So like that, there are other developers that have made this possible. So MicroSim suite of tools contain now a GP solver in NPI based, and then you have got GP solver in open form based, GP solver in Android based. So you have got a FD code that is handwritten with NPI calls, or written in a shorter form using the open form library calls, and written in Android to exploit the domain decomposition across the CPUs. So you can see the GPU model has been transferred. So you have also got KKS model implemented both in CUDA and OpenC. And now we are actually in the process of converting the OpenC solvers into simple. So in one of the upcoming releases, you should be able to see the KKS simple model based. This is already discussed in the context of thermodynamic coupling, so we will not have to do that now. So we will proceed further. Okay, so the demonstration is taken care of in the hands-on session. So we will still that. Okay. So we have got some. So where do we need to pick up these tools? It's already mentioned. Yes, we pick it up from the public repo or from the website MicroSim repo. And then we have a YouTube channel which is also linked to the MicroSim.org website, which contains the playlist for each of the workshops. So every workshop we record all the videos and so here are some examples of simulations which are possible. Let us have a look at them. We just see some of them have already been shown. Second one is about 2 elements. Going to the competitive. So these kind of simulations are very global in MicroSim. The right one actually is a very heavy computational 4,000 cross points and several thousands of course analysis to capturing the quantitatively the irrigation protocols as well as the morphology of features. Here is again a simulation showing you in 3 dimensions how the precipitate evolution takes place. The example system chosen was related to the supervised, which equally only elements this time. And you will also have that in several hundreds of precipitates being considered now. Studying the course and elastic effects also. Alright. So the publication that we saw in the beginning, 2025 competition with science. The work that has gone behind it is, I think, the first of its kind across the world, namely benchmarking different phase-field models in a single population. So usually you will see that every research group follows one of the models and then uses it for data. So here we have a very interesting situation where we have used all the models, implemented them, benchmarked across them, and compared it. So this is also to showcase that the underlying physics of these models is actually the same, giving you the same output. That's one thing that is mentioned, and also the implementation with respect to the different space of capturing the thermal mix is what is the function of the system, and quantitatively matching them to show you that numerically also they are actually comparable. So this is actually a very unique exercise. I don't think such an exercise has been done in the past. So here is again the comparison across solvers. All the solvers are giving me the same sort of kinetics which is the which is again very significant. And the discretion schemes also. So if you see the 3 versions of GP solvers, one where the discretization is finite difference method by hand using objects. The second is left to open form, which is taken care by the libraries of open form, and the third is ambient scale connection. Different types of bit spacings within the domain. Domain decomposition is done across the processors. So all the 3 have actually very different kind of discretizations, but all give you the same results, which is again one very important outcome. This study showing that the way you solve the libraries you use, as many as the methodology is one. And the scalability of this solver also has been shown. So this was done on the Parameter in IISc on a day when the entire cluster was available. So it was done using the 4761 CPUs and it's a big domain, 2000 times 2000 points. So the left side simulation is done in 3 hours the configurations, and on the right hand side you have got the domain actually with 2 by 2, 4 times the different spaces. And you can see that when we use 4 times the number of CPUs, the computation time remains the same. So which means that now here I want to also present to you that the commercial phase-field simulation software doesn't scale even beyond 8 cores. We're talking about here 19,000 CPUs. So definitely scalability is something that we can definitely be proud of in these solvers. Okay, and then whenever we do the studies using scalability with API libraries, one is always asked to give you what is called strong scaling and weak scaling. So strong scaling means you fix the domain, the problem size, and as you keep on increasing the number of CPUs, the time taken for the problem to solve should come down. And in weak scaling, you have got something different. That is, you keep increasing the size of the problem as you increase the number of CPUs, and you should take the same amount of time. So both the kind of scalings have to be performed because it's not obvious that left hand side will go down and right hand side will stay flat automatically. what will happen is that between computations, if there is too much of communication, the scaling won't come, and that will show up. So here is where the scaling is pretty good, and this is also to showcase that the API implementation of the code. I think if you could see every API code is actually very. And the scaling also is very differently suited for Android solvers. This is again giving you beautiful scaling both strong scaling and weak scaling regimes. So the multiple solvers are actually having this. And then we come to a specific problem in an alloy which is of high importance for the aerospace industry, the single crystal silver alloy that is used for blades. And this alloy has two many components. It's an 11 component. And there have not been any simulations in the literature taking all the elements into account. Usually, one would have taken say 3 or 4 elements that are largely present in the alloy and then run the simulation with it. And here we have taken all the elements into account and perform the simulation, which is actually, I think, the first time again in the literature. Okay, so you can see the energetic evolution of the alloy. And the segregation pattern between these arms is very important. Super alloys. For some elements, it will actually lead to detrimental phase formation. So, loading segregation is very important. So, today that can be calculated quite accurately for all the elements by taking the thermal. So, this is a very expensive simulation and hitherto not done by any other solver. Now, this has already been benchmarked in a different simulation, not 11 elements, but slightly less number of elements. I think 6 elements. Mohan's work has benchmarked the spacing as well as the segregation. So already we know that our solvers are capable of predicting the spacing and the segregation reasonably well. So here are the segregation patterns with the morphological features for all the 10 species that are there calculated. And so this is again very rare. You do not have all of them taken into account: aluminum, cobalt, chromium, iron, tungsten, aluminum, cadmium, silicon, and everything you see there.
Rhenium.
So then we also added some additional capabilities to the MicroSim suite of tools where we optimize the flow near the segregation plant. It's very important because the segregation elements happen exactly at solid liquid interface, and the elements are different density, so there will be convection happening in the liquid, and that convection actually can affect the morphological pattern formation also. And it leads to certain defects which are very detrimental for the segregation growth. For example, fractals. Fractals are defects where you have got a channel formation where the morphological evolution starts to stabilize with the channel, and the channel is going to be remaining as a defect later on. So such a blade is of no use. You have to just throw it. So you have to grow the same crystal without channel formation, which means understanding the convection patterns that are happening is very difficult. So ability to simulate them correctly also is important, and that is again not there today in most of the. It is one situation where it is being done. So what's the pattern here? So as the front is moving forward, how the velocity profile is evolving. We will have, I think, the vortex mentioned in another video. So, but that is actually already taken. So, vortex formation and its motion in the liquid in front of the solid liquid phase have already been taken. So, I think this is there. So, here is where we have got the pattern formation, and then slowly the convection in the liquid would be taking place, and we have this starts to move around. The initial stages of the channel. So you can start seeing the vortex formation here. Slowly you can see that it is picking up momentum. It moves forward. Okay, I can see one more here, one more here. Okay, so they are picking momentum, which is driven by the gravity. Gravity is in the horizontal direction. And the density difference is what is left. So this convection pattern is actually now affecting the morphological evolution of the solid itself. And how this vortex will actually move around and affect the channel formation is the key to understanding the Fermi formation. So this kind of a simulation where on the left hand side the solidification that is happening is with multi-components up to 10 elements. And on the right hand side, you have got a liquid in which solidification fluid is taken account using the lattice volts method. This kind of a coupling actually these are also very expensive simulations in terms of computational. Alright, so you can see that as these vortices start to interact with each other, they start to collaborate and they start seeing that they start to open up in space and start to sort of give signs that metal formation can be understood very soon if we can do this at a much larger scale. So this is some development which should be exciting, and the work for this beautiful module also is getting completed. I think the publication also will be done very soon. After that, others also should be able to then explore the similar kind of studies themselves using these open source software. All right, so we'll move forward. So this is again a set of simulations to show the cathodic process. Here we chose the Arman green system, and here is a example where we look at the cooling rate effect. Cooling rate effect, and showing the grain formation, and each grain that is forming is actually releasing the rate. That is actually taken into account to form the curve. So we can say that here is a situation where the coupling is actually upwards. That means the phenomenon that is happening at a micro scale is telling you what will happen to overall. That is actually very interesting. Usually, those such simulations were made in the past, where the imposed cooling rate is actually then directing the here we are going to look at that by taking the effect of what is happening here, and that these open form simulations are then compared with the Shile. It's not like Shile is correct and we are coming close to it. It's not true. Shile is actually restrictive in its assumptions. The reality is more closer to what the situations are showing. Shile is only one extreme edge, which is rather than the lever rule assumption. So it's only telling you one limiting case for you to see whether the simulations are always the same to us. So here you see start seeing the grains that are growing slowly, and each grain will then start becoming the gain, right? And here you can see that eventually the liquid is finishing off with the. So here I want to also tell you one success story, which it looks very similar. So that was a case of MTech student who did this simulation for a company in Chennai. They were looking at the heterogeneous integration of aluminum hydrogen by reducing the gas bubbles of. So argon is actually at room temperature, and when you bubble it through, right? So you are basically causing this simulation. And depending upon the rate at which those bubbles are created, the grains are going to be or lower density. So the student Lakshman Rama has done these simulations and performed it as a study, and they have the actual work also done in a automotive company in China. And when you compare those microstructures with these which are simulated here, for instance, brains with genetic history of communication along with it, actually talking for the industry, they were very thrilled. They never saw something like that. And they were all using only tools like this, diagnosis, which is only for a toxic simulation for thermal process. It only predicts some hotspots or something. But they never saw actually that you could see great structural transmission. So, diagnosis will not do it, but it's not meant to do it either. So I have a feeling that the software tools that we are developing through MicroSim suite of solvers are actually capable of very, very useful simulations for the again, let's study where we have seen those multiple points and microstructures coming out of the here again we have got the same solvers implementation the precipitation of the aluminum modeling system. So different variants of the precipitate can also be taken down.
This is also dendrite. This is just ternary. Yeah, both are dendrites. It's just a ternary.
Oh, yeah. So it's just a repetition of whatever unknown thing we are repeating on nickel aluminum.
What was the composition?
We have not noted here, but we have chosen in the nickel column.
It's a nickel base.
It is an approximation of a nickel base. The reason was the nickel aluminum model thermodynamic data was very early. So our earlier exams are all done with nickel. But by now we already have these simulations possible on nickel aluminum.
Actually, look at the nickel aluminum. I didn't see the effect itself, but it's a nickel rich furnace, so that expensive. Yeah.
Yeah. Okay, so we have the studies that are also visualized in the Python tool to look at the brain size and the function of time and all these kind of statistics are available. The hands-on session will show you how to visualize them yourself. The presentation studies also done in multiple different alloys, and
all of these are movies.
okay. So here we have, so here is the way variants are coming. So there variants, different precipitates having different orientation of those, histographically of this. Some of the presentations also take into account. So you can start seeing what will happen when more variants are present in the system. And you also have you have got different type of variants.
But there are movies you can play with.
So you will see some kind of a correlation of the variants that are arranging themselves in certain configurations. So these are also the some situations these are also understood closely using the various surface energies. Variants, so we should start forming Mercedes-Benz logo and such. Yeah. Approximately in 3 different levels. Okay, so also the brain growth was taken into account. This is again a general solver. And I think this is the theta.
No, this is the FD.
We have both solvers. One where we have one case field per brain, and then the other way we have got a orientation of current So both of them have been implemented. So it's done on both the 2D and 3D as you can see. The left hand side is the 2D weight problem, and the right hand side is the 3D weight problem. So both have already been. And we have, so also we have got the orientation of the grades in 3D dimensions. It's really good coordinates so that we can represent the orientations completely. And that has been implemented in open form and format. So we have some of those also. You can see the different orientations of the grains is really growing. So has been mapped. So there are some features that are available in the post-processing tool where we can see that, for example, when we look at the grain growth, each of the triple junctions can be detected automatically. And they can be extracted. So you can get the triple junction locations output, analyzed for some other purpose. So we had actually done some analysis of whether graph learning that can be done on those in the data, etc. So one can extract features out of these simulations and then perform some learning. So the post-processing is becoming richer with the more and more automatically measured and parameters can be measured. And then in the case of 3D, particle. So it's so as many measurements that can be automated are being automated. And here is a situation where you have a solidification simulation, and for a small part of the domain, you also want to do. So the initial domain for the precipitate simulation, you want to not see it yourself, but you want it to come from the solidification, so that the simulation effects can be done. So that kind of a thing is also being done here. So you have.
It can split and play it.
Yeah. So here we show how we go about the kind of a. So you take the segmentations. The domain is taken into 4 parts. You choose which of the parts you want to zoom further, and then go on and on again. So that way, what happens is that you have the initialization data for the precipitate simulation coming straight from our simulation. Now, you may ask, why can't we do the same thing right away? But it's humongous that. The length scales over which the solidification simulations are there are actually much larger. And precipitations are actually very, very small, so the grids cannot just compare. So you will not be able to do precipitation simulations on the same domain. You have to take only a part of the domain. But choosing them directly from the output and using it as an input for the next simulation is now possible. This again is not a feature in many of the softwares. Even in, I would say, commercial software for ACM, these are not so. For example, let us say I do a deformation of a sheet. On the deformed sheet, I want to do a welding. And the welding should take into account the digital stress given by the deformation. Now, I will tell you how many of you actually are doing entrance simulation, understand very complex. It is not clear. Passing on the output of one simulation as an input for another simulation is not very clear, but we have attempted that using one of these requirements. All right. So we have got again the state simulations where the dendrite center and dendrite tip are used for the simulations. So you will see that dendrite tip will have a different composition, segmentation, the center, and so there should be a difference in the state density and sizes from the tip and the center, and that has to be visible. Segregation does play a role when it comes to precipitation in superprocess. So no wonder the precipitation heat treatments are so very complex. They actually need to homogenize so that the dendrite informations removed as much as possible before they go to the precipitation. Here is where again we have done something interesting recently, where using the 3D printing, the scale of the index can be very small, so we should take advantage of this cursor competitions to make the statement very fine. That we could do with this. Yes, but simulations are actually confirmed about that. Here's a summary of the features of different suite of solvers. And so all of them are three-dimensional, and you can downgrade them to two dimensions by just changing one parent in file. So which means that you don't need to have solver that is separate from 2D and 3D. You have just default is they're all 3D, and they support different architectures of making them high performance. One of them is the message passing interface library based calls that are there in different method solvers, and then the open form software library which is originally meant for PFD, but then they are adapting it to solve the physical equation. And then the CUDA and OpenCL libraries which are for the GPUs, CUDA from NVIDIA for NVIDIA hardware only, whereas OpenCL which is for NVIDIA or AMD or Intel in the CPU or GPU. So these solvers are all basically being developed and benchmarked and compared. And then we have also done the brain growth module using graphical solver. The hammer solvers are now implemented the GP method very extensively, and that's again a very big jump because they are highly scalable and they are giving this scalability across the multi GPUs, so which means that you now have multiple ways of utilizing the GPU capability. You have got CUDA, you have OpenCL, you have hammers. Types of libraries which we use. In materials community, how many software tools can actually take advantage of GPU system is a question. The question mark. So there we are actually now very strong. And of course, 4% tools have been made to particularly measure the quadruple points, triple points, and then size of the states. And then they have also got the sequential multi-scale tool to use the output of a tool as input for the specification tool. Different solvers using the same data. And singularity images for installation are to be helpful for those who are starting. So we recognize that the user community will get different stages of development. Some users are getting started, so for them it's important to just run the cases as it is and see how the output is. For them, singularity things are very useful because you don't have to do any kind of installation. You just install singularity, copy the images, and you can start to run the solvers as long as the hardware is supporting that. Okay, and once you are used to it, you want to then run these solvers on computer. You can also do that with singularity, but then we encourage you to learn a bit more so that you can compile the code yourself on the supercomputer to take advantage of the images that are being generated time for the particular hardware that you are going through. So similar images are basically to ease the initial learning curve, but we encourage you to learn further to compile the software supercomputers. The software suites are such that most processing, pre-processing is done with the GUI computing. And if you have a powerful enough workstation, you can actually do everything using the GUI itself. You don't have to go over the mission. But we recognize that many of these are to take advantage of supercomputers, so the computational code can be offloaded to the supercomputer. That's something that we encourage users to try as soon as. And of course, the flow modules have been integrated. The writing codes and method is used for the flow simulations, and that will be integrated. So with that, I thank you for your attention. We have about 5 minutes of an overview of it. We have hands-on session coming up. We will be able to elaborate some of the pieces that we work on.
So you can ask questions in the chat.
Participants are welcome to ask questions in the chat box. We will answer in the next step.
Huh?
Do we have the hands-on at 8:50?
8:45. Yeah, we'll 8:30.
So yeah, I think the online participants can take note that we will have a dinner break here at 7:30 to 8:30, and hands-on sessions we will start again at 8:30. So there we will be able to clarify some of the doubts we have right now.
Sir, is there any comparison, like the GP model is there in Amrex, OpenFOAM and FDM? So do we have any comparison for the simulation results of these things?